Hi there. Welcome to part 3 of the analysis, design, and simulation of a forward converter. Okay, let me go ahead and review a little bit. It's been a while since I done part 2. In part 2, I showed the technique of analyzing a 2-switch forward converter. Uh, in this case, I have a schematic, and the 2-switch forward means that it would have two MOSFETs, one switching the top portion and one the bottom, and with the transformer to provide isolation. And then you have your forward diode, which is D1, and then your catch diode, which is D2. So basically D1 operates when the primary is on, so you can think of that as being on when it's T on, and then D2 is turned on when it's T off. In other words, when the primary MOSFETs are turned off. And then you have a low pass filter, which is this here, L and C, and then of course your load resistance. And I showed how depending whether it's T on, meaning the MOSFETs, primary MOSFETs are turned on, you break up a schematic into its components, and then you also do the same thing when the primary MOSFETs are off, which is T off, and you write two equations that describe the voltage across VL. Okay, and then you use the volt-second rule. Okay, you use the volt-second rules to equate the voltage across the inductor during T on and the voltage during the inductor during T off. And you end up with an equation, and basically you end up with this transfer function, which is V out is equal to input voltage Vn times NR, which is the turns ratio, and then D is the duty cycle of your PWM. Okay, so now there's some more definitions that I need to define, and the first one is this one. Okay, continuous mode. Okay, continuous conduction mode. What does that mean? Okay, typically this is the operation mode that we desire. Okay, we want to operate in a continuous conduction mode, and typically, and sometimes you'll see the books call it CCM, continuous conduction mode. Okay, and basically what it means is that the output inductor always has current. And you might say, well, what do you mean by that? I'll show that graphically in a little bit. Okay. Now the opposite, or I guess the complementary of that, would be if, and let me go back, and when I say output inductor, I'm talking about this. I call that your output inductor. Okay, so basically in a continuous conduction mode, there's always current flowing through that inductor. Okay, in continuous conduction mode. Okay, now you have the other extreme, and that is defined by this, which is discontinuous conduction mode. And typically this is not desired. Okay, and you'll see books call it DCM, conduction mode. And what does this mean? It means that the output inductor its current, okay, I goes to 0. Okay, in other words, there's a point where there's no current in the inductor. Okay, so let's take a look at that a little bit. Here's two graphs, and this is continuous conduction mode. Okay, and if you were to plot or actually get a scope and an ammeter, a clamp ammeter probe connected across the output inductor, you would see a waveform that looks like this. It ramps up to a certain peak and ramps down, and it continues this pattern. Okay, so this is the pattern that it sees. Okay, now if you take the average, which is this green line, okay, that average is actually your I out. Okay, you can call it I average as well. Okay, now if you notice, this is 0. Okay, and this is IL minimum right there, and it also has a max. So during its conduction time, T on, the inductor has current, and then when it discharges, it also has current. It never goes to 0. In other words, this minimum never touches the 0 axis, basically. Never touches the 0 axis. Okay, so graphically, that's what it means, that this point or the minimum part of the waveform is always above the x-axis. Okay, now in this continuous conduction mode, which is this here, I'll just put mode there. You can have a situation where you start from 0. Okay, this is 0, this, and it goes to a certain max. Okay, but then during T off, or the time that the MOSFET is off, this is T off, this is T on. So during the time it turns off, you can have a situation where the current in the inductor actually goes to 0. So during this time, there's 0 current, no I in the inductor. Okay, and typically this is bad for us when you're designing a forward or a buck, because when you enter a discontinuous conduction mode, you get a phenomenon where you peak detect. Okay, basically, if you want a output regulated at, let's say, 3.3, and if you allow your current of the output conductor to go to 0, it will start peak detecting, and this V out voltage would actually go up high, and in many cases it may go to 3 to 4 times bigger than what you actually desired, and you may damage capacitors, electrolytic capacitors, if you don't rate them high enough, or it could actually damage loads. So you don't want to operate in this mode. So basically, don't want that. Okay, so you always want to operate in a continuous conduction mode. So that's the main idea that I want to show as far as conduction mode. And here's another note that I made, that as RL, in other words, the load, this is the load, as the load increases, I out decreases. In other words, this average starts getting lower, and there's a particular point where you're just above 0 right there. Okay, and they call that the boundary condition. Okay, so basically you want to operate above the boundary condition. Okay, and that's to avoid this phenomenon, the peak detection. Okay, so let's take a look at again in more detail and kind of describe the waveform. Like I mentioned, the waveform is actually going to look like this in red. Okay, and if you were to take the average, you get this IDC. Okay, and this is actually, you can also define it as I out or I average. Okay, so basically this waveform is the current that is in your inductor. Okay, so what I'll put is it's approximate. You can think of it that it's the I out plus a current with an AC component. Okay, that's an AC component. So basically this ripple is your AC. Okay, and this is what this schematic is attempting to show, that this current IL, okay, so it's basically a combination of a DC voltage, and again this is I out, or you can also call it I average. Okay, this DC, typically you want to go to your load. Okay, that would be I out. You can also say that it's the I average or IDC. Okay, and you want this AC component to go through the capacitor. So I'll put AC component. Okay, and with that as being known, you can actually set your ripple specification. Okay, now typically in a power supply, when you look at the specification of a power supply, it's not unusual to see a specification of 1% of the full voltage, okay, or lower. So I'll put or lower. Okay, and the example that I'm going to be using is I will be designing for a 3.3 volt supply. So 1% means that I will be designing for 3 millivolts of ripple, peak to peak. Okay, so with that being known, if you know that your ripple is 33 millivolts. Okay. And you know what your ESR is, then you can design for a certain current, a delta current. Because this AC ripple, the delta I, when it flows through this circuit, the capacitor is assumed to be extremely low capacitance. In other words, X of C is 2 pi F C. Okay, we assume that this is going to be big, very big, which means that X of C is going to be small. And basically you want it basically 0 ohms. Okay, so for analysis purpose and for design purpose, we can think that this capacitor is a short. Okay, therefore the ripple that you would see across this node, assuming that the capacitor is a short, is going to be V ripple. It's going to be the AC current times ESR. Okay, which is what this equation is. Okay, very important. Okay, now the design of the output inductor affects the ripple voltage. Okay, so there is a rule of thumb that you can set the delta I, basically this delta, you can set it from 10 to 40% of your full load. Okay, so if your full load is 1 amp, okay, we can set the current to anywhere from 10%, which would be 0.1 amp, all the way to 0.4 amps. Okay, so what I'll go ahead and do is, to make this a little bit more understandable, it's always better to do an example instead of just going through the lecture and through the algebra. It's much easier to just design something. Okay, so this is a design example. Okay, my input minimum, I'm going to select this 26 volts. Excuse me. Okay, and I'm going to design for an output voltage of 3.3 volts, which is going to be right here, 3.3 volts, and I want an I out of 1 amp and a ripple of 1%, and it'll be 1% of 3.3 volts. Okay, and I'm going to assume a duty cycle of 46%. Okay, so the first thing that we want to do is to calculate the turns ratio. Okay, so how do we do that? Well, we've already derived the transfer function. Okay, this is V out, this is the turns ratio, and I'll put a little R there. This is a duty cycle, and the duty cycle that's set by the PWM, and of course this is my input voltage. Okay, now if you solve for D, you end up with this equation. Okay, And what I did is actually V out divided by V in minus D. Okay. Now, to make it a little bit more accurate, I know that the voltage is here, but since I want to know what the secondary is, I went ahead and added the drop across the diode to get a more accurate turns ratio. Okay, and so you end up with V out minus VD. Okay, now in this case I'm going to be using a Schottky diode, and the one that I will be using is the 1N5822, which has a approximately 3.69 volts voltage drop at 1 amp. So that's where this number comes from, right there. And let me make a little correction. It's supposed to be plus. Okay. So when you plug in, the number is 3.3 plus 0.369 divided by the duty cycle and V input. So I end up with a I didn't carry out the math there. Let's go ahead and it should be 26 times 46, 1196. So you end up with a turns ratio of 0.306. Okay, so that's the first thing you want to do. Okay, calculate the turns ratio. So that sets the turns ratio of your transformer. Now the second step is you want to calculate the voltage across VL. Well, when I'm talking about VL, I'm talking the output inductor. Okay. Now we know that this node is V out, and that's going to be 3.3 volts. Okay. So now we kind of have to calculate what is the voltage at that node. Okay. And if you think about it, we know what the voltage is going to be at the secondary. We know that it's going to be Vn times the turns ratio. Okay. And then what we do is we subtract this voltage drop from the forward, which is accounted right there. Okay. So basically this is the left side, or the dotted side of the inductor, and then this is the right side of the inductor. So that's the voltage across the inductor. Okay, so when we plug in the number, we have a delta of 4.287 volts. Okay, then step number 3, I choose the delta IL in this example. Okay, made a little mistake here. Let me see. Okay, notice that this is supposed to be 1 amp. So let me go ahead and do the math again. 1 amp. So that means that this is going to be incorrect. This is going to be 0.1. 0.1 amp. 10% of that should be that. Okay, so excuse me. Let's calculate. Oh, let me define this a little bit. Okay, since it's going to be 1 amp. Okay, now the third step, or the fourth step, is calculate the value of L to get that ripple voltage or current. So we use the voltage equals L times di dt. We solve for L, so you end up with this equation. Okay. So now we just plug in the numbers. We know that we want a voltage, and this voltage comes from this voltage that we calculated there. We know that we want a delta T of 4.6 because this comes from the 46% duty cycle, and we're operating at a frequency of 100 kilohertz, which is 10 microseconds, so that comes out to 4.6 microseconds. So that's where this comes from. Okay, so we'll go ahead and do that. Say 4.287 times 0.0000046 equals divided by 0.1, and that's 56. So that would be 197 microhenries. Okay, is that correct? 6, yes, 197 microhenries. Okay, so that's that. So now we know what the inductor is. Okay, so now I make my spice. I know that I have to change that to 196 microhenries. Okay, so now we can go ahead and go to the spice simulator. Okay, so this is a circuit that I'll be using, and instead of using MOSFETs, I'm using a switch. Okay, so this is a switch, and I can define the parameters of the switch by this dot statement. It's a dot model, and I named it SW MOSFET, and it's a V switch. And when you enable this line, it will turn on the switch, and it will have a R on of approximately 100 microohms. Okay, and when it turns off, it will have a resistance of 10 meg. And basically, it turns on when you have a voltage greater than 10 volts, and it will turn off when you have a voltage less than 2 volts. Okay, so you have this top switch, and then you have this bottom switch. Okay, now here are your primary diodes. I've explained what these do. They're used to clamp the voltage when it resets. Okay, and this is the inductor, primary inductor, and I defined it with a curly brackets, and I defined it as LP, close curly brackets. Okay, and this is my my iron core, and this defines the coupling coefficient, and what it does is it couples L1 and L2, and the way you couple these two is by putting in L1 and L2, and then the third is supposed to be the coupling coefficient. Now, a coupling coefficient of 1 means that it is a perfect inductor. So for simulation purposes, I'm just going to assume that it's a perfect inductor or transformer. So I put a coupling coefficient of 1. Okay. Okay. And then L2 is the secondary. And if you know what your NR is, the turns ratio, which we already calculated, then it's easy to calculate the secondary. Okay, because the secondary is going to be LP times the turns ratio squared. So what I did is LP times NR1 times NR1. So that's the squaring function. And since LP is a parameter, I have to define it. NR1 is a parameter. And of course, I define those here. So to define them, you put a dot param, LP equals 1. So in this case, it means that the primary is going to have 1 millihenry. And this is just for simulation purpose. I'll go through a design of the transformer on a later lecture. Okay, and then this is the turns ratio that we calculated. So I define it as a dot param NR2 or 1, and it's 0.306. Okay, and then for my input stimulus, I defined the voltage that will turn on the MOSFET. So the initial value would be 0, pulse 12 volts, time rise 10 nanoseconds, fall time 10 nanoseconds, and then to define the pulse width, I basically define it as a parameter again. And to define a parameter, you put the curly brackets, and it's duty cycles divided by frequency, close curly brackets. And the period is going to be the reciprocal of frequency. And again, you define it by putting the curly brackets. Okay, so I think I have everything here. And let me see. And here is the 1N5822, which is Schottky, another Schottky. And right now, I'm not simulating for ripple. I just want to get a plot of the waveforms. In the next lecture, I'll show you how to set or design the output inductance. Okay, and I believe that's about it. So I need to change this to 196, I believe. Okay, then I do a transient. Okay, a transient, I set the step time to 1 microseconds, and I wanted to stop at 1 millisecond, and I'm putting a step ceiling or the maximum time step of 10 nanoseconds. So that will give me enough resolution. Press go. Okay, so here we have the simulation. Okay, and I'll go ahead and zoom in here. And this is the ripple voltage. I designed it for 3 volts. So I have a ripple. Let's see. It's about 73 millivolts. Okay. But the important waveform that I want to show is this. This is the current through the inductor. Okay. And like I said, if I was to take the average, set it right there, and then go to position, average, which is mean, the average is 1.007. Okay. So that's very close. Now remember, the delta from positive and negative was supposed to be 100. Let me see. It was supposed to be 100 milliamps. So I will do a Y2 minus Y1. And if you see here, it's 98 milliamps. So indeed, we designed it with the proper amplitude that we wanted. So basically, let me go ahead and get rid of that. these are the two waveforms that I want to show. So this is the ripple, V ripple. And this is the current through the inductor. Okay. I can go ahead and then copy that. And there you go. So basically we designed that. So I think for now I'll go ahead and stop here, and then I'll go into further detail and show you the steps in how to actually design for a 33 millivolt ripple specification. Okay, thank you for watching.